Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And today we're going to talk about one of the most controversial technologies, and that is nuclear energy. On one hand, we have people that say that nuclear energy could be the white knight. That is, if the atmosphere is beginning to warm up, no problem. Uranium does not create carbon dioxide, so let's go nuclear. That's one point of view. Another point of view is, well, take a look at the track record of nuclear power. We had 3 Mile Island in 1979. We had the Fukushima disaster just a few years ago, and we had Chernobyl back in 1986. And nuclear power is on the ropes. The Wall Street Journal is among the most anti-nuclear of the various organizations that are out there because of the fact that costs have soared for nuclear energy. So with us today to perhaps give us a more larger perspective is Tim Judson of the Nuclear Information Resource Service. Website is NIRS.org. And let me be very frank about this. It's very polarized. On one hand, you have the nuclear industry saying that nuclear energy will become so cheap, it'll be too cheap to meter. On the other hand, you're talking to the environmentalists who say that it's an unmitigated disaster. So let's be clear, NIRS is a clearinghouse for anti-nuclear organizations. Later, perhaps we'll have a pro-nuclear organization on Science Fantastic to give a different perspective on the whole subject. But as I said before, in this hour, we're going to take an overview of nuclear energy. First of all, nuclear power plants do not explode like a Hiroshima bomb. Let's get that very clear. In order to have an explosion, you need to have pure uranium, about 90% enriched. 90% pure uranium is what's required in order to get a bomb detonated on, let's say, U-235. However, a commercial nuclear power plant is like a wet firecracker. That is, it uses only 3% enriched nuclear energy, which is enough to create heat, but not enough to create a runaway chain reaction like in Hiroshima. So how do you extract energy from radioactive rock like uranium? Well, when you put it into a reactor, it heats up. 3% enriched uranium will cause it to rise, and it boils water. Water surrounds the nuclear core, and as it boils, the boiling water is shot through a turbine, which spins the blades of a turbine. And the spinning blades turn magnets which then push electrons inside the coil, and bingo, you get electricity coming out. So in other words, it's a very expensive way to heat water. Boiling water creates a thrust of steam. That thrust is then pushed against the blades of a turbine, and the turbine blades in turn create electricity just like in a dam, or for that matter, just like in your bicycle generator. Your bicycle spins, it pushes against a magnet inside your generator, the magnet then spins, and the spinning magnet pushes electrons inside a wire, and bingo, your bicycle light lights up. So in the same way that your bicycle light lights up, nuclear power plants create electricity. Now, what's the problem? Well, there's several potential problems. One is that if you lose the water, then the rods begin to heat up until the rods begin to melt. Now, it's not going to be like the movie China Syndrome, where they talk about melting all the way down to China. It's not going to do that. However, it will cause the containment structure to melt, and the uranium will then go right into the ground, perhaps creating a steam explosion or a hydrogen gas explosion, like what happened at Chernobyl. Back in 1986, we had a hydrogen gas and a steam explosion that blew the lid right off the top of the Chernobyl nuclear power plant, and roughly about a third of the core was lofted into the atmosphere, which became fallout, radioactive fallout, which then sailed over Kiev, sailed over much of Eastern Europe, and even sailed over the United States of America in very tiny form. So we see what could happen in case of a nuclear accident. At 3 Mile Island, it was a simple loss of cooling because of human error. They didn't see the fact that water was draining from the core at 3 Mile Island back in 1979, and the core suffered a meltdown as a consequence. One of the worst, however, was Fukushima, where we had not one, not two, but three melted nuclear power plants whose core liquefied. We've never seen that before, by the way. We've seen cores melt, but we've never seen a 100% liquefaction of 3 cores simultaneously at Fukushima. And the disaster is going to go on for decades. It's estimated that maybe 40 to 50 years worth of agony to begin the process of cleaning up the mess at Fukushima. So, with us today once again is Tim Judson of the Nuclear Information Resource Service in Washington, D.C., and we're going to talk about nuclear energy, pros and cons, and we're also going to talk about what the Trump administration has or does not have for the future of nuclear. And if you want to get on over 100 radio stations that carry Science Fantastic, give us a call. The hotline number is 866-323-2129. Give us a call and perhaps your thoughts will be heard on national radio. So once again, today we're going to talk about nuclear energy. Will it save us against global warming? Is it the white knight? Or is it a Trojan horse in disguise? Stay tuned as we continue our discussion of nuclear energy.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again on Science Fantastic, we profile some of the most amazing developments in science and technology that are going to touch our lives. And today we're talking about a very controversial technology. We're going to talk about the future of nuclear energy. For example, what will the Trump administration do given the fact that some people think that nuclear could be the white knight to save us against global warming? Other people think that it's a black hole that'll simply eat up the economy and not deliver on its promises and endanger the population in the process. With us today is Tim Judson of the Nuclear Information Resource Service. Their website, by the way, is nirs.org. And let's face it, in this business, things are polarized. Either you're for or against nuclear energy. And let's be very clear, NIRS.org is a clearinghouse for anti-nuclear information. Later, we'll probably have a pro-nuclear guest on Science Fantastic to give us an opposing point of view. But first of all, Tim, could you explain a little bit how you personally got interested in the nuclear issue and tell us a little bit about NIRS itself?
Sure. Well, thanks, Professor Kaku, for having me on the show. It's really a pleasure to be, to be able to have a chance to speak to you and to talk about these issues.
Mm-hmm.
Well, as you said, my name is Tim Judson, and I'm the executive director at a nonprofit organization called the Nuclear Information and Resource Service. I've been here at NIRS for about 3.5 years. I've been actually, working on issues around sort of public interest policy around nuclear power for about 18 years, and I really got started as a person living in Syracuse, New York, which is near 3 nuclear reactors, concerned about the effects of nuclear power on my local community and the risks that it posed. And there were a number of really significant safety issues occurring at those reactors near Syracuse, the 9 Mile Point and Fitzpatrick reactors, that had a number of people in my community very concerned. And as we began to push for safety improvements and for the closure of those plants, I learned a lot more about the industry and about wide-ranging issues from the impacts of the nuclear fuel chain, from the mining of uranium all the way through to the generation of nuclear waste, and the impacts that nuclear power has on the environment and on local communities, as well as other energy issues, including renewable energy and the potential for the transition to a clean energy economy. NIRS has been around since 1978. We were really founded as an organization to provide people at the state and local level with reliable, sort of unbiased information about nuclear power and radioactive waste, and to be able to help local communities, deal with the impacts of nuclear power and radioactive waste facilities, on their local environment and their local populations. And so we've been doing that job for 38 or going on 39 years. The relevance of our work has unfortunately remained constant throughout that time.
Okay, well, let's just jump right into some of the controversy around nuclear power. First of all, Indian Point. Right here in New York City, we live in the shadow of a nuclear power plant, and one government study done in 1980 called CRAC-2 estimated that a complete meltdown at that reactor, and this is a government study now, would cause property damage up to, if you add up all the details, $300 million in 1980 dollars. So we're talking about potentially billions of dollars in property damage. However, the pro-nuclear people would say that this government study is only a worst-case scenario. But now the Governor Andrew Cuomo, has stepped in and said that he is going to phase out the Indian Point nuclear power plant. So tell us a little bit about Indian Point.
Sure. Well, Indian Point is a reactor site, as you mentioned, that's 25 miles north of New York City on the Hudson River. There's been concern about Indian Point, since the beginning. There are 3 reactors at Indian Point, only 2 of which are still operating. But the first one was opened in about 1961, which was a reactor that was built actually without backup safety systems, and couldn't meet any of the modern licensing and nuclear safety criteria, and was shut down in the 1970s. But the other 2 reactors at Indian Point are much larger and started up after that. And Indian Point is 2 miles from the or 1 mile from the intersection of 2 earthquake fault lines, which wasn't known about when the facility was originally sited. The design of the reactors, the engineering of them, wasn't built to withstand the kind of earthquake that can happen around Indian Point. And 17 million people reside or work within 50 miles of Indian Point. And there's really no feasible plan to be able to evacuate that population in the case of a worst-case nuclear accident like Fukushima or Chernobyl. Basically the entirety of New York City is within the 50-mile radius of Indian Point. And for some context as to the relevance of that number, the Obama administration recommended that all Americans within 50 miles of the Fukushima Daiichi nuclear power plant in Japan evacuate, in the wake of the tsunami and natural disaster there, or nuclear disaster there 6 years ago. And so that's is sort of a sense of the scale of the immediate impact of a nuclear power plant accident that can take place. And so a number of public officials, not just the governor of New York, but the attorney general and many local politicians, have expressed a lot of concern about the wisdom of having an operating nuclear power plant so close to New York City with so many people that would be at risk. And frankly, given the role that New York City plays, the metro New York area plays within the national and even the global economy, the immense national risk that a nuclear accident at Indian Point could pose. And not just from the potential for a nuclear accident or nuclear meltdown, but the danger of Indian Point would pose as a potential target for malicious activity like a terrorist attack. One of the reasons that the officials in New York really woke up to the danger of Indian Point 16 years ago was that one of the jets that hit the World Trade Center flew directly over Indian Point, and it was later discovered that Indian Point had been considered as a potential target for the terrorist attacks that took place on 9/11.
Now, in case there was a terrorist attack on Indian Point or a meltdown, the population of New York City is, about 8 million or so people. In the greater 8.5 million, and in the greater New York area, you're talking about perhaps double that, maybe like 15 million people if you have a large compass that sweeps the entire area. And that's a good fraction of not just the population of the country, but a good chunk of the economy of the United States as well. So wouldn't a terrorist attack or a meltdown at Indian Point cripple the U.S. economy as well as endangering the lives of tens of millions of people?
That's right, and the risk doesn't just stop there. I think you mentioned the estimate of the economic losses from an accident at Indian Point in the Crack 2 report from 1982. It was actually $300 billion, not $300 million, was the estimate of the damage then. And of course, with inflation and real estate values having increased in the last 35 years since then, the estimates now are potentially $1 trillion or more in economic losses that could occur just from the loss of usable property within the kind of the fallout zone of an accident at Indian Point. But the issue with nuclear power plants in general and Indian Point in particular isn't only from the reactor itself melting down, as we saw happen at Fukushima and Chernobyl. But at nuclear power plant sites in the U.S. in particular, there are pools of water called spent fuel pools where the waste, the nuclear fuel that's removed from the reactor is stored on site. And at U.S. reactor sites, and Indian Point is no exception to this, because we have no national solution to the long-term management of nuclear waste, they've continued to store all of that waste on site at reactors in increasingly dense configurations. So at Indian Point, you have two fuel pools that are full of still extraordinarily radioactive and hot, used nuclear fuel that have 5 to 6 times more radioactive material in them than in the reactors themselves. And so an accident involving a fuel pool at Indian Point could have an even greater effect than a meltdown at the reactors. And so you have a sort of a compounded risk that these reactor sites pose. And and when you consider a place like Indian Point, that's you sort of get a sense of the unimaginable scale of what a disaster or a malicious attack on a nuclear plant could entail.
Now, there's a precedent for this in the fact that the Shoreham nuclear power plant in the heart of Long Island was canceled by the governor. And if you take a map of the United States and you see Long Island as this very long piece of real estate coming out of the United States, and you put a nuclear power plant dead center in the middle of that island, you realize that it's impossible. It's just physically impossible to evacuate millions of people across the bottleneck. And then, of course, once you leave the bottleneck, you hit Manhattan. Wouldn't that be the worst nightmare if there was a nuclear accident right there in a place of Long Island?
Sure, that's right. And I think what you mentioned with Shoreham, this was a reactor that was actually built in the 1980s for a cost of in 1986 dollars of over $5 billion. That was a very expensive project, and that site, despite the complete impossibility of evacuating the local population in the case of an accident, that reactor was sited and licensed by the federal government, and was only stopped by the then Governor Cuomo of New York, and basically required a bailout of the Long Island Lighting Company, the local utility, that the ratepayers are still paying off today. But I think obviously, an act of wisdom on the governor's part to have stopped that reactor before it really started operating. And, the dangers with Indian Point have always been very similar. Indian Point is on the mainland, but in an area that has small roads and is constrained by mountains and, and has traffic, really extreme traffic jams just on a normal afternoon. Never mind, if everybody in Westchester County and the surrounding areas were trying to get out and flee from a nuclear disaster and go to pick up their kids at their schools, and and people that would be stuck and waiting for mass transit to come, all those sort of problems that could occur that people in the local population have really become attuned to.
Okay, now the pro-nuclear people would say yes, but it's not going to happen. So after the break, let's take a short commercial break, and after the break we'll talk about Fukushima and about whether or not our reliability probabilistic studies are accurate or not to predict a nuclear meltdown.
This is Science Fantastic.
technologies that's going to come right to the fore because President Donald Trump wants to rearrange our energy priorities. So with us today is Tim Judson of NIRS, Nuclear Information Resource Service, and you can go to their website at nirs.org. And later on, perhaps we'll have another guest who will talk about a more pro-nuclear point of view. So, Tim, tell us about Fukushima. Why were the Japanese caught off guard? Didn't they plan for it? I mean, nuclear power plants, of course, are relatively safe. A day goes by and nothing much happens at a nuclear power plant. But what happened at Fukushima?
Sure. Well, I think the thing to kind of keep in mind about nuclear and power in general is that, from the beginning, there's been a deep recognition that operating a nuclear reactor poses a significant safety risk. And, even in the 1950s, as the U.S. government was beginning to promote nuclear power both here and abroad, they had to address some very sticky questions about that. And one of them, obviously, was the risk of a nuclear accident and the kind of damage that could impose. And so what the U.S. did from the very start was pass a piece of legislation called the Price-Anderson Act, which essentially has been a law that's been in place for 60 years now, that limits the liability of nuclear power corporations that own and operate reactors from the financial liabilities that they would face from a nuclear accident. Essentially, it sort of caps the industry's liability at currently about $13 billion, but essentially commits the federal government to pay for the damages and liabilities that exceed that. And in Japan, at Fukushima, you kind of see what the scale of that could be. We've talked about Indian Point, where upwards of $1 trillion for an accident at Indian Point would be the impact. At Fukushima, the estimates early on about the cost of the damage from the cost of recovering from the accident, we're in the many tens of billions of dollars. The government released an updated cost estimate in December that the cost of the cleanup and recovery from the Fukushima disaster is going to be at least $188 billion now. And so this is a risk that is well known within the industry that is quite significant, but that is generally a risk that's going to be borne by the public because the industry could never obtain a level of insurance that they could buy for themselves to absorb the impact of an accident. So in Fukushima, what happened, was the other thing to remember about nuclear power is that because of the enormity of the risk that's entailed, reactors are supposed to be designed with redundant safety systems, to high degrees of engineering expertise and precision, to be able to account for and operate safely on a daily basis. But because of the nature of the technology, when things go wrong, things can go very, very wrong. And that's where problems with the wisdom and the interests of the regulators and the government and the industry can really be at cross purposes with nuclear safety. And so in Japan, obviously Japan is well known to be a region subject to a lot of potential for natural disasters, from volcano eruptions to earthquakes. Engineering standards for buildings in Japan are among the highest in the world because of the frequency of large earthquakes there. And people in Japan had been raising concerns about the vulnerability of nuclear power plants to earthquakes for decades. But the government essentially, at the behest of the utilities, which had invested many billions of dollars in building and operating their nuclear reactors, essentially, spent more effort assuring the public that things were safe than in actually taking safety precautions. And so what happened at Fukushima was entirely predictable, but the government had ignored the risk and had not made the industry take measures that would have been necessary to mitigate the risk. So what happened at Fukushima was, obviously there was a large 9.0 on the Richter scale earthquake on March 11th, 2011 that shook the site, but actually wasn't the cause of the nuclear disaster. What happened was... Okay,
Tim, we're going to have to take a short commercial break. And after the break, we're going to get into the autopsy of what happened at Fukushima, blow by blow. And what's next for 3, not 1, not 2, but 3 melted nuclear power reactors.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about perhaps one of the most controversial technologies of modern times. We're talking about nuclear energy, its past, its present, and its future. With us today is Tim Judson of NIRS, Nuclear Information Resource Service. Their website is nirs.org. And where we last left off, we were just beginning to talk about the Fukushima disaster, where a tsunami overwhelmed the safety systems of these nuclear power plants, causing three nuclear power plants to melt down. A 100% melt in all three reactors, a liquefaction process that we've never seen before at a commercial nuclear power plant. And what is the status of the cleanup? First, you have to stabilize the system by getting the cooling water to circulate. Then you have to remove the melted core. But Tim, how far are we in this process? Aren't we really at the very early stages of stabilizing the reactor accident?
Yeah, it's hard to really say whether we're even at the beginning of a true cleanup and recovery at Fukushima. We're 6 years past the accident. Only really one thing of significance has been done since the accident happened, and that was the removal of irradiated fuel from the fuel pool at the number 4 reactor on the site, which happened about 2.5 to 3 years ago. But in terms of the three, just to give a little bit of background on the site, Fukushima Daiichi is actually a 6-reactor site. But at the time of the accident, only 3 of those reactors were operating. The other 3 were shut down for refueling. And so all 3 of the reactors that were operating melted down. The 4th reactor, had been shut down, and the freshly removed fuel was in the pool, and so still very hot. And there was a danger, and there was a really strong concern in the weeks after the accident that there could have been a loss of water in the pool at Unit 4, and that fuel could catch fire and create an even bigger disaster. Luckily you saw the images in the weeks after the disaster, or days after the disaster, where they were pumping as much water as they could, pumping and dumping as much water as they could into the pool of that reactor to try to prevent that from happening. The easiest thing they've been able to do so far, which wasn't easy at all because the building was so damaged, was to get that fuel out of the pool at Unit 4 before the building was in danger of collapsing, and to move it into another storage site on the ground. But as far as the 3 reactors that melted down, there's been virtually no meaningful recovery of those sites at all. In fact, the owner of the plant, Tokyo Electric Power Company, or TEPCO, still does not know where the fuel that melted out of the reactors is on site. There are some indications this week that they may have gotten a camera in that identified where some of the melted fuel might be in the number 2 reactor, but they haven't even been able to get a robot in close enough to be able to tell whether that's actually the nuclear fuel or something else. Essentially, inside the reactors, where these accidents took place, the radiation fields are so powerful that every time they sent in a robot to try to inspect, the robot's electronics have been fried out by the radiation fields, and they haven't even been able to determine the status of the internals of the reactor well enough to even begin planning a cleanup of the site. Now, this is compounded by the fact that Fukushima, the nuclear plant, is obviously right next to the ocean, but because Japan is mountainous, there's a lot of water that flows down from the mountains through the in the groundwater of the reactor site. And so for the last 6 years, there's been about 300 tons of water a day.
Tim, we're going to have to take another short commercial break, and after the break, we're going to continue with the discussion of the horrible mess at Fukushima.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, in this hour, we're talking about the future of nuclear energy. With us today is Tim Judson of the Nuclear Information Resource Service, NIRS.org is their website. And we just finished a discussion of Fukushima. And I should also point out that the United States Pentagon has gotten interested in this. They set up a DARPA challenge, challenging the robot specialists around the world to create a robot that could clean up the mess at Fukushima. All it had to do was get into a car, sweep the floor, turn a few valves, and do things that even a child could do. And the results were horrible. Only one entry was able to finish the required goals of the challenge, and it basically showed you that, well, robots are not going to be able to clean up a mess like at Fukushima anytime soon. Well, let's move on, because I want to talk a little bit about the arguments of the pro-nuclear side. And they say, yes, nuclear power plants are potentially dangerous, but we're getting better at handling nuclear accidents. But what about global warming? After all, just look outside. The weather seems to be changing. Even farmers know that. Summertime is about a week longer than it used to be. Every farmer knows that. So the question is nuclear the white knight? So, Tim, what are your thoughts?
Well, global warming is obviously, one of the greatest, problems that humanity faces at this point. I mean, whether you, believe that human activity is the sole cause of it, the scientific consensus, among more than 99% of the scientists that study the issues is that human activity is contributing to global warming, and that we need to take measures to reduce the amount of carbon dioxide and other greenhouse gases that we're emitting into the atmosphere. And so, given a problem of this scale, we have to be practical about how we're going to approach solving it. And the reality, and so there's, we clearly need to transition to non-CO2, non-carbon dioxide emitting energy sources. And so this is a space in which the nuclear industry has really tried to promote itself, as a source of electricity that can generate without the direct burning of fossil fuels. The problem that we have is that we have to look at, what's going to be a practical way of addressing the problem. And that means, technologies that can be deployed quickly enough at an affordable enough cost, that we can actually reduce emissions quickly enough to mitigate the impacts of global warming. And nuclear power fails those tests. The reality is that nuclear power has proved to be too expensive and too slow and too unpredictable to be able to provide, reductions in greenhouse gas emissions and fossil fuel use in any meaningful way. So, for instance, there was a report out this week from The Economist magazine that showed that of the 55 nuclear reactors that are being built in the world right now, 35 of them are years behind schedule. And I think if you looked at it, most of those would also be way over budget. And, when energy analysts compare the costs of different sources of energy, nuclear power is by far the most unattractive option available. And in fact, Wall Street investment firms declared years ago that any energy company that decides to invest in building new nuclear power plants was going to be downgraded at, and in some cases near to junk investment grade for taking on such an unwise risk. Now, by contrast, we've seen the cost of renewable energy sources and energy efficiency, falling at astronomical levels. That the cost of solar power is now 5 times less than what it was, just 5 or 6 years ago. And the same thing has happened with wind energy, and energy efficiency is by far the cheapest energy resource that we have. And so, what we really see happening is that, both just in terms of how rapidly and how quickly and how affordably renewable energy and energy efficiency can be deployed, we could actually, have a much better chance of dealing with the climate, crisis with a transition to renewable energy sources than we can with investments in nuclear energy. And this is becoming an increasingly sort of immediate issue, because at the same time that building new nuclear power plants has proved to be a total failure in the U.S. and elsewhere. The existing nuclear reactors that we have in the country are getting so old and needing so many upgrades and repairs in order to be able to continue operating, or to even be operating safely. That the cost of them has gotten so great that the reactors are closing just because they're simply uneconomical to operate. And so we're facing a situation in a number of states, including New York, where the choice is really before us. Are we going to invest billions of dollars in subsidies and bailouts to prop up the existing group of nuclear reactors, or are we going to put our eggs in the basket of renewable energy? And I think when you see the evidence of what the costs are for these different energy sources and the number of jobs that can be created in transitioning to cleaner energy sources, from our standpoint, the conclusion is pretty clear that we ought to be investing in modernizing our infrastructure and in moving to cleaner energy sources, and not in propping up nuclear power or trying to build new nuclear reactors.
Okay, well, even though the Trump administration does not have a complete, detailed overall energy strategy, what is your thinking? You're in Washington. What is your thinking about what the Trump administration will do with regards to nuclear?
Sure. Well, the Trump administration seems to be very clear that the environmental impacts of energy sources are not going to be, a consideration for them in determining energy policy. And so, there's been rumors since Trump was elected that he is going to pull out of the United Nations climate agreement that the U.S. signed on to a year ago, and that climate change is not going to be a factor in their decision making.
So, wrapping up, we have to wrap up. So, has the Trump administration given us any indication as to what its nuclear policy will be? Yes or no?
Yeah, so Trump has been known to be pro-nuclear for a long time. One of the signals that we got that there's reason to be really concerned about the direction that the Trump administration is going to take. Okay, Tim, we run out of time. Once again, you're listening to Science Fantastic with Professor Michio Kaku.
This is Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we throw the lines open because this hour is your hour. Okay, well, without further ado, let's jump right in because it's open mic on Science Fantastic. Let's take the first listener phone call.
Okay, so I have a question that I've kind of had for a little while now, and everybody I've tried to ask hasn't been able to answer it. And I've been a big fan of yours for a long time, and I've often thought that it would take somebody like you to answer this question. So I figured I'd ask you. So with the sound barrier, it's the compression of the sound waves, as I understand it, that causes that resistance, and once you break through that, you break the sound barrier, sound boom, etc. Well, with the speed limit of light, is that caused because of a light barrier? Is it a compression of light or something similar to that, or maybe time is related to it in a sense? And if you were to break that light barrier, would you go back in time, or what do you theorize would happen? Thank you. Bye.
Well, the answers to your questions were all worked out in 1905 by a young physicist who was 26 years old by the name of Albert Einstein. He couldn't get a job being a physicist, but he worked out the theory of relativity, which answers all your questions. First of all, you're right that the sonic boom in an airplane or jet takes place as you approach the speed of sound. All the sound waves begin to compress in front of you, and as you hit the speed of sound, you break through the compression of all the waves that have then squeezed in front of you, and that creates the sonic boom when you break the sound barrier. Now, scientists used to think that perhaps that's the way it worked with light, that light also has a sound barrier of sorts, and as you break through the sound barrier, well, maybe you can't, and that puts an upper limit to the speed of light. Well, we now know that all those theories are, in some sense, wrong. Just before Einstein proposed relativity in 1905, there were a lot of schemes like what you just proposed. People thought that the ether, that is, the substance that fills up the vacuum, was sort of like a fluid. And yes, you would have sonic waves in this fluid, and yes, you would have all these bizarre properties as you approach the speed of light, and therefore, experiments were done to measure this effect, and they found none whatsoever. You know that if an airplane moves toward you, away from you, at an angle, that the airplane seems to travel at a different velocity. But light is different. If a flashlight points toward you, a flashlight points away from you, or you throw the flashlight into outer space near the speed of light, the speed of light of the flashlight is the same. The same no matter where you point the light beam, light always travels at the same velocity. How can that be? It was Einstein who finally figured it out. It's not the compression of a substance that causes all these bizarre properties. It's not the electromechanical stretching or compression of an ether that explains the Michelson-Morley experiment. It's that space and time itself can be altered, compressed, that the faster you move, the slower you get, and the more compression takes place. Space itself is compressed as you move in the forward direction and as you approach the speed of light. That's just the way it is, independent of the properties of the ether. According to Einstein, ether may or may not exist, that is a substance of the vacuum, but it is irrelevant. It's not measurable. It has no measurable effects. Now, sometimes people say, well, how can that be? That violates common sense. If you throw a flashlight toward you, against you, you shine a flashlight at an angle, the velocity of light should change. Nope, it doesn't change at all. That violates common sense, but hey, the universe doesn't care about your common sense. That's just the way the universe is. We measure it every day with your GPS system. Every day your cell phone depends upon all these bizarre distortions of space and time. Get used to it. That's just the way it is. Einstein comes out on top for the last 100 years. Okay, let's take the next listener phone call.
Yes, my question is in regards to the colonization of Mars. I was wondering on your thoughts on the use of mushrooms on Mars due to their positive reaction to radiation, and seeing as how there's so much radiation on Mars. Thank you so much. Bye.
Well, if you saw the movie The Martian, you realize how difficult it is to grow anything on the planet Mars. First of all, the atmosphere of Mars is very cold. Most of the time, the planet itself is frozen solid, so you can't grow anything in the soil because you hit permafrost almost immediately. The atmosphere is made out of carbon dioxide, which is good for plants. Plants love carbon dioxide, but it's extremely cold, and there's no soil. There's no soil to speak of, because where does soil come from? Soil comes from the decay of previous generations of plants. But you see, there are no previous generations of plants on Mars, and so it's difficult to raise plants on the surface of Mars, which is frozen solid. Now, you mentioned mushrooms. Mushrooms, in fact, will grow in damp environments, but not if it's frozen solid. So the first thing you have to do is somehow unfreeze the surface of Mars. And that requires you to change the atmosphere of Mars or to have other schemes to inject heat into Mars. One suggestion is to have gigantic solar panels in outer space orbiting Mars, shining and concentrating sunlight from the sun down to the surface of Mars, heating up the surface. So in other words, use solar collectors in outer space orbiting Mars to focus sunlight on the surface of Mars. Elon Musk, the billionaire behind Tesla Motors and SpaceX, he advocates using hydrogen warheads, hydrogen bombs, to perhaps begin the process of melting the polar ice caps, which are made out of solid carbon dioxide and solid water. So yet another mechanism is to inject methane gas. Methane gas is a greenhouse gas. It is 20 times more volatile than carbon dioxide in terms of capturing sunlight. And so methane gas has been proposed as one way to accelerate a greenhouse effect on Mars. So in other words, it's all great, these ideas about putting plants on Mars, but first you got to thaw out the frozen permafrost and get some soil before you can plant anything on Mars.
Yes, Professor Kaku can help you with your homework. He can even help you with your kids' homework. But only if you ask. This is Science Fantastic. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. That's right. Why simply listen to the radio when you can be part of the radio? Why not give us a call? The hotline number is waiting for you right now. Okay, well, let's move right along. Let's take the next listener phone call.
Given what we are doing to our home planet, do you think we have reached a level of intelligence where we should colonize other planets? Or should we wait until our species maturity level matches our own intelligence?
Well, you ask a pretty heavy question, but let me say this. The main limitation to colonizing the planets is really not a question of our maturity, because, of course, our civilization is quite primitive and quite young when compared to an advanced civilization. The real problem is, well, cost and the mechanics of the colonization process. I mean, let's be fair about this. We're not going to be able to colonize the planets for centuries. That is, in this century, in the 21st century, we'll just begin to have the first outposts, perhaps on Mars, perhaps a permanent colony on Mars by the end of this century, but not booming cities, not gigantic civilizations on Mars. No, just a few outposts on the red planet. Now, in the next century, once we have robots, that can do a lot of the heavy lifting, that can perhaps even self-generate and create self-generating robots, at that point, perhaps the first cities may begin to be formed on the red planet. But to create a real civilization on the red planet will take, on the scale of centuries, because of cost, because of the enormous distances and hazards involved. Now, you ask a very probing question. Are we really mature enough to handle this? And, well, as Einstein once said, our technology has outraced our humanity in the sense that we have all the ways in which we can split the atom, we can sequence the gene, we can begin to manipulate life itself. But hey, we can't even figure out simple things like immigration or income inequality on the planet Earth. So, in other words, we have a long ways to go before we become mature. But when could we become mature? Well, as a scientist, we believe that energy is the way to measure the progress of a civilization, at least the gross way in which to measure a civilization's progress. And we are on this scale a type 0 civilization. We get our energy from dead plants, oil and coal. But by the year 2100, we should become a type 1 civilization. That is a civilization that harnesses truly planetary power. We're talking about the creation of a planetary civilization, a civilization that is multicultural, that is scientific, that enjoys freedom, a civilization that is planetary. That's called a Type 1 civilization. Type 2 civilization is like Star Trek. It is stellar. It actually controls the energy output of an entire star, like the Federation of Planets on Star Trek. So Star Trek would be a typical Type 2 civilization. And then a Type 3 civilization is galactic, like Star Wars. The Empire would be a typical Type 3 civilization. So you see, on this scale, we're a long ways from being able to colonize a planet because we're still basically a Type 0 civilization. But the most dangerous transition is between Type 0 and Type 1. A Type 0 civilization still has all the savagery, all the sectarianness that typifies its rise from the swamp. And however, by the time we become Type 1, we have a shot at maturity, a shot at creating a truly planetary civilization. Okay, well, moving right along, let's take the next listener phone call.
Hello, I was wondering why time is considered a dimension. I understand that we have 3 spatial dimensions, X, Y, and Z, and we can access those dimensions at any time. But time seems to be a weird dimension because we're forever stuck in this present, and I want to know why that is considered a dimension, why it's considered our 4th dimension. Thank you.
Well, your question would require a book to answer, but we'll take a crack at it after the commercial break.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question that is pretty much impossible to answer during the duration of a radio program. However, let me give you some basics about time. First of all, we say that time is the 4th dimension. Now, what does that mean? That means it takes 4 numbers to typify any event. So if you want to meet, let's say, somebody for lunch in Manhattan, you would say, meet me at 12 o'clock at the intersection of 42nd Street and 5th Avenue on the 10th floor. So it takes 4 numbers, 3 numbers to specify space, 1 number to specify time, and any event can be categorized, therefore, by 4 numbers. So that's why we say that space is 4-dimensional. But that said, time is different from the other dimensions. You can freely go in space. In the X direction, you can go forward or backward, left or right. However, time is different. Time, you can go forward, but going backwards is very difficult. You would have to do all sorts of, you would have to create all sorts of havoc with space and time in order to go backwards. And mathematically, we say that that's because space-time is elliptic. That's the mathematical way of expressing it. And using the mathematics, we get bingo. Every time we get it right once we use Einstein's theory of space and time. Now, then the next question is, why? Why is it that time is different from the other 3 dimensions? That is, it takes 4 dimensions to typify any event in the universe. But while space, you can go back and forth easily in space, you cannot easily go back and forth in time. And, well, the short answer for that is we don't really know. Now, the highest theory of space and time that we have, that even includes Einstein's theory as a subset, is string theory. But even in string theory, we simply put in the nature of space and time. In string theory, instead of having 4 dimensions, we have 11 dimensions. That's right. We think that the original Big Bang took place in 11 dimensions. So when people say if the universe is expanding, what is it expanding into? It is expanding into not 4, but 11-dimensional hyperspace. But even in these 11 dimensions, time is still special. And why is that? Well, it turns out the string theory is not mathematically consistent unless you have at least one of the dimensions become elliptic. And so, well, that's not really answering the question in words that can be expressed in English. But mathematically speaking, string theory itself is inconsistent. Inconsistent unless time is different from the other dimensions. By the way, if you want to see the mathematics behind this, get a copy of my book, Introduction to Superstrings and M-Theory, and you can see the mathematics behind everything I just said. Okay, well, moving right along, let's take the next listener phone call.
Yes, I would like to know if there's such thing as the future, as if the future is a movie that's already been pre-recorded that we just don't know yet, or if the future is a probability spectrum where anything can happen and there is no specific future that is going to happen, whether we know it or not. Could you make that distinguishment and explain that, please?
Okay, I think you're getting the inspiration for your question from the movie The Matrix. The movie The Matrix stimulated a lot of philosophical discussion, even among scientists, about the question, well, is the universe a simulation? We know what a simulation is, to simply take a videotape, put it in your computer or your DVD, and bingo, all of a sudden you have people dancing and laughing and acting as if they were living in a real universe. But we know, of course, that it's nothing but a simulation. It's called a video. And then the next question is, are we living in a video? And if we are, could we ever know it? Can we create an experiment that'll determine whether or not everything you see around you is an illusion, whether it's been uploaded into your brain? Now, you know the movie The Matrix. In the movie The Matrix, reality as we see it, as we visualize it, is actually a computer program, a videotape. And we think we have free will in that videotape. But this universe of ours was created by aliens that conquered Earthlings and have reduced Earthlings to batteries. That's our function, to create electrical energy for the machines. Now, here's the question. Do you know, can you create an experiment that'll prove or disprove whether or not you're in a simulation? My personal point of view is no. Maybe you are. Maybe reality is all an illusion. Maybe you're in a dream and you'll wonder when you're going to wake up from that dream. Well, how can you make an experiment that'll tell the difference? Personally, I think that is, quote, beyond science. And after the break, I'll add a few more words to that. The question is, can you prove things like, is the universe a simulation? Or what about reincarnation? All these questions, we're going to say a few words after the break. We're going to continue discussion of, well, is reality a fake? In other words, are we living in an illusion?
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour, so why not join the fun? Jump right in. Give us a call at 866-323-2129. Well, before the break, we had a question that is actually rather difficult to answer, and that is the universe a simulation of some sort? And again, if you're a fan of the movie The Matrix, you know how difficult it is to tell the difference between a simulation that is uploaded into your brain and reality itself. Now, science is based on things that are testable, falsifiable, and reproducible. That is the essence of what science is. However, there are things that are not testable, not reproducible, and not falsifiable. That doesn't mean it's wrong. It just means that it doesn't fit with our usual conception of science. For example, reincarnation. Sometimes at a cocktail party, you may meet somebody who swears that they are the reincarnation of Cleopatra. And you give some simple questions to test their knowledge, and of course they get all the answers wrong. But then they say, well, you see, the history books are wrong. How do you know the history books are wrong? Because I am Cleopatra. I lived through it. I know the history books are wrong. At that point, well, end of discussion. There's no progress you can make because you cannot falsify that statement. If someone claims to be Julius Caesar, well, how do you falsify that statement? Because if they get all the facts wrong, the person says, well, I am Julius Caesar. That's why I know the facts are wrong. In the same way, you cannot create a test that'll test whether or not reality is a simulation or not. Maybe it is. Maybe it isn't. Now, the questioner also asked a question about quantum mechanics. Is the future determined, like in a videotape, or is the future probabilistic? That is, many possible futures that can exist. Well, if the universe is a simple videotape, then the answer can be made, and the answer is it is not possible. That's because we have quantum mechanics. Quantum mechanics says the universe is not determinable. That is, there's always a probability that the universe could go in a different direction. And we see no deviation from quantum mechanics at all. So the short answer is the world a videotape? And the answer to that is no, because the videotape is deterministic. Quantum mechanics is not. But can that whole thing be a simulation? Well, the short answer is I don't know.
Does he know about string theory? He wrote the book on it. You're listening to Science Fantastic. Here's everyone's favorite physics professor, Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, it's open mic on Science Fantastic. Okay, well, moving right along, let's take the next listener phone call.
I was just listening to the professor on the radio. He was talking about the expansion of the universe and comparing it to the surface of a balloon, and that there was no center spot that we know about for the origin of the Big Bang. And reading about astronomy, I was reading about Professor Edwin Hubble and redshift and how he pointed his telescope toward the other expanse of the universe, and he noticed that the universe is not only expanding, but it's expanding at an ever-increasing rate. My question is, what direction did he point his telescope? And if the universe is on the surface of a balloon, how does it have any depth in order that he can determine that it's expanding at an increasing rate? I'm quite confused by it all. If Hubble's theory was right, there must have been some kind of an origin, because what if he was pointing his telescope at the other side of the balloon relative to the universe as it exists on the surface of the balloon? I'd appreciate an explanation if that's possible.
Yes, well, you ask a question because many people are often confused by the discovery of Edwin Hubble. Back in the 1920s, it was so simple when you talked about the universe to an astronomer. The universe was the Milky Way galaxy. End of story. Period. The universe was the Milky Way galaxy. And the Milky Way galaxy itself was maybe 100,000 light years across. But then, as you pointed out, here comes Edwin Hubble that finds that there are other galaxies out there, that our galaxy is just one among billions of other galaxies, and then he calculated the speed at which these galaxies are moving, and he found that they were moving away from us. No matter where you pointed your telescope, in any direction you point your telescope, all the galaxies are moving away from the Earth. So either the Earth is the center of the universe, which we don't believe, or the universe itself is expanding. So again, use the analogy of a balloon. If you're on the surface of the balloon, then an ant would see all the other points of the balloon moving away from it. So if you were to paint stars on the surface of a balloon and put an ant on the balloon, the ant would see all the dots moving away from it. But then if you were to ask the ant, where did it all come from? From what point did the expansion take place? At that point, the ant would say, the question makes no sense. I can only see what's on the surface of the balloon. That's it, period. There's nothing else but the surface of the balloon. Therefore, to the ant, the center of the balloon makes no sense. The center of the balloon is beyond the comprehension of the ant. Well, in the same way, where did the center of the expansion take place? Was it to the left, to the right, up, down? No. You cannot point to a direction in the universe and say that's where the Big Bang took place. Now, there are two ways you can look at this. You can either say that once upon a time the universe was very tiny, even space itself was very tiny, like a little ball, and it exploded in all directions as a consequence. Therefore, in some sense, where did the Big Bang take place? All around us, because the universe itself was tiny. The universe itself was very small at the beginning of time, and so where did the universe expand from? Everywhere. Because if you're an ant sitting on a tiny, tiny ball, and you ask, where is the center of that tiny ball? The ant would say, everywhere. But now the universe is expanding in a very large way, and another way to look at it is to say that the universe is expanding in another dimension. At that point, the ant says, I give up. I don't understand this other dimension because my eyes can only see in 2 dimensions. Well, that's where Einstein comes in, because Einstein says that perhaps there's a 4th dimension, and the universe is expanding into hyperspace, into a dimension that we ants cannot visualize. Okay, well, moving right along, let's move on to the next phone call.
Hi, Dr. Kaku. My name is Emmanuel. I was a physics teacher for 2 years at the high school and MCAT level. Unfortunately, don't know a lot about electronics, and I got a C in Calc 2. But I wanted to ask you, what do you think of Tesla's theories of transmitting power through the air? Do we really live in a world of plugs when all our technology could be absorbing energy through the air? Thank you.
Well, you ask a very interesting question, because Nikola Tesla, of course, was one of the great pioneers of the electronic age. It's a very sad story. Many of his patents were more or less stolen from him. He never got the financial rewards that he deserved because he was sitting on a ton of extremely valuable patents, and he did not have a fleet of lawyers to protect them. And so pretty much the electronics industry got off the ground without him, which is a very sad tale. Now, Tesla had some great ideas, but he also had some strange ideas as well. He was trying to basically communicate with Martians. He thought that you could create ray guns, which we think we can create, but with laser beams, which was beyond his technology. And he thought you could shoot electrical energy through space. It turns out you can through what is called induction, but it's very inefficient. You can perhaps, for example, recharge your cell phone battery from a distance, but it's very inefficient. And it may not be too helpful either, because, of course, you are shooting electromagnetic radiation through the air in large quantities. But in this sense, Tesla got it right, that, yes, you can, in fact, use what is called induction to shoot electromagnetic energy through the air. And that's how some people actually charge up their cell phones, by putting the cell phone next to this recharger without any wires at all.
You're listening to Science Fantastic with Professor Michio Kaku. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to celebrate the 50th anniversary of the Star Trek series. That's right, it's hard to believe, but it's been 50 years since the Star Trek Enterprise blazed the way for science as well as science fiction. And with us today to talk about the 50th anniversary is the author of Star Trek, the official guide to the universe, Andrew Fazekas, who is a commentator with the Canadian Space Agency and Canada's Weather Network channel. Author of the book Star Trek, the official guide to the universe, with a foreword from William Shatner and over 400 full-color illustrations in that book. You know, we have to look at the relationship between science and science fiction. After all, the greatest astronomer of the 20th century was Edwin Hubble of the Hubble Space Telescope fame. And he was destined to become a country lawyer, but as a child, he remembered reading Jules Verne. And because of his romance with Jules Verne and all the books talking about the exploration of the oceans and the universe, Edwin Hubble dropped his job being a country lawyer, went to the University of Chicago, got a PhD in physics and astronomy, and went on to discover the expanding universe, which eventually led to the Big Bang Theory. Not to mention the fact that Edgar Rice Burroughs, author of the Tarzan series, wrote another series called John Carter of Mars. A young boy by the name of Carl Sagan read that book, and he said, wow, he wanted to go to Mars. He wanted to go to the Red Planet and chase after Princess Dejah Thoris, just like John Carter of Mars. And Carl Sagan went on to become an astronomer. So many times, children, inspired by science fiction, go on to become professional scientists. Many scientists at NASA, for example, can swear that it was watching Star Trek on TV in the 60s and 70s that launched their career in the sciences. Now, for me, it was a little bit different. I remember watching Flash Gordon every Saturday morning, and for me, hey, I was hooked. By that time, I already knew I wanted to become a physicist. I was reading everything I could about Einstein and the unified field theory. But then watching Flash Gordon explore the stars and the heavens every Saturday morning, I said to myself, wow, starships, cities in the sky, what's not to love? Even George Lucas got his inspiration for Star Wars by watching Flash Gordon. Well, once again, you're listening to Science Fantastic with Professor Michio Kaku. Our special guest will be Andrew Fazekas, author of the book Star Trek, The Official Guide to the Universe, the 50th year anniversary.
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to dedicate it to Star Trek. That's right, to Star Trek. Did you know that it's the 50th anniversary? And there's a book called Star Trek, The Official Guide to the Universe. So today we're going to talk about the Star Trek universe, not the universe of actors and actresses and production studios, but the universe, well, the real universe, the universe of stars, planets, and galaxies. And with us today to talk about Star Trek, The Official Guide to the Universe, is the author, Andrew Fazekas. He's also known by his popular nickname, the Night Sky Guy. We should say that he's a science writer, broadcaster, and he's a regular contributor to National Geographic News. He's a correspondent with the Canadian Weather Network channel and a consultant to the Canadian Space Agency. So, Andrew, glad you could be on Science Fantastic.
It's great to be here. Thanks for the invite.
Okay, first question that we always ask our guests is, how did you as a youth first get interested in science?
Wow, you know, it's I really have to give props to my dad on that one, because from a very young age, he introduced me to all kinds of sciences and nature. My dad is a medical doctor and also a cancer researcher, and so I was very fortunate to be able to go into his lab, his biochemistry lab, and see the things that he had, all the wonderful instruments like scintillation counters and microscopes and all kinds of neat things that he had in his laboratory. So that really sparked an interest in sciences as well. But also, he loved going out camping, and so my dad and we would go out camping and fishing a lot. Growing up in Canada, we've got wonderful nature here, and we would go out to the backwoods and go on to very remote lakes in Canada and go fishing in the summertime, and sitting around the campfire, looking up at the stars. My dad would basically teach me the constellations and the mythology associated with it, and point out really interesting things. So, the astronomy and nature, learning about the land and the earth and sky, it came from a very, very young age, and it just followed me throughout my life.
And when did you get your first telescope?
Wow. Well, my father bought his telescope when I was very young. I would say I was 6 years old. He bought a department store a little Newtonian reflector telescope with a 3-inch mirror, very modest instrument. But we had fun with it. We lived in downtown of Montreal, Canada, in an apartment building, and we would go up to the 14th floor rooftop, and he would show me all kinds of things. He introduced me to, I remember seeing, probably I must have been around 6, 7 years old, to see the moons of Jupiter and the cloud belts of Jupiter, the rings of Saturn, all the wonderful craggy surface of the moon as well, touring it like like the Apollo astronauts. I imagined myself at the point, looking through the eyepiece and seeing that all those wonderful, craters on the moon. It was just a fantastic thing at 6. And then by the time, and this interest in astronomy just kept going and going throughout grade school, and my dad sort of finally gave in. I think he was watching to see how interested I was in astronomy, and just wanted to make sure that it was going to stick. And then at the age of 12, he bought a Celestron 8-inch Schmidt-Cassegrain it's quite a nifty instrument with a drive, a mechanical drive to follow the stars, and that's it. I was really hooked, and I started doing, like little projects on variable stars and looking at comets and, of course, the planets. And back then, and this was in the early 80s, there was no computers, no apps on iPads to figure out where the planets would be. I would actually bring out my calculator and calculate out where the planets would be, where the moons are going to be visible. It was just a fantastic time that really opened my mind to the universe.
And I should also point out that I'm a physicist, not an astronomer, and I took my telescope out, and I didn't know where the hell I was looking at. I didn't know where the stars were, where the planets were, and I kind of gave up. Now it's all computerized, right? You just point the telescope in a certain direction and off you go. But I said to myself, I'd rather be a physicist than an astronomer. But I guess you can do both.
That's right. Now we've got the go-to telescopes. You just punch in the name of the object, and off the telescope whizzes and just beeps when it gets there. So it takes the challenge, I think, though, out of the search, the quest to actually find it. The hunt. The hunt is really, I think, part of the fun. So when I, as an astronomy educator now today, I try to encourage people to make sure you learn the sky, learn your way around all those wonderful constellations, because it'll make it that much easier to, when you take that telescope out, to find your way.
Now let's leave the universe as it actually is and talk about the Star Trek universe. It is the 50th anniversary of Star Trek. Hard to believe. And there's a book, The Star Trek Official Guide to the Universe, by Andrew Fazekas, who's with us here today. So what steered you in the direction of the Star Trek universe?
Well, I think that goes back to my childhood, because, as I said before, I was, introduced to astronomy at a very young age, and that really is in connection directly with Star Trek, because at the same time, one of these rituals that my father and I did was watching Star Trek episodes. And this was back in the early 70s. So I guess it must have been one of the first times they were rerunning the original series with William Shatner and Leonard Nimoy from the 1960s. So that was the first reruns, and I was watching them on Sunday mornings, and it was something that we just did all the time. I would scoot into bed with my dad and watch it in the morning, Sunday mornings, and I would barrage my dad with questions on and on about what's this going, what I'm seeing on Star Trek, what are those planets and stars, and how is this possible, how are they getting where they get. And I think I just beat my dad down, and that's when he got a telescope. And so that connection between astronomy and Star Trek goes back back to grade school. But then flash forward, as a young adult, I became a very dedicated amateur astronomer, and I loved doing astronomy outreach, and that involved, with my local astronomy club, I would go out to do public events and bring out my telescope to show people the stars, the heavens. And what I noticed very quickly is that to really engage the general public, if I would invoke Star Trek analogies and showcase objects that I became familiar with in my in Star Trek, in my viewing of that series, and then just sort of pick out a few objects that have real life counterparts, and just talk about it in terms of Star Trek to the people, that really engaged them, made them very fascinated. And so I began to put together a list of objects that was visible within the Star Trek universe that had real-life counterparts to them that I would be able to show at the telescope. And that really became I feel, the seed, I guess, of the basic seed of the book.
I should also confess that when I was a child, I used to watch Flash Gordon on Saturday mornings. Of course, there was absolutely no science whatsoever in Flash Gordon. It was all fantasy. But again, it sets you off on a journey. George Lucas also says that it was Flash Gordon that set him off to create the Star Wars series. So now, let me ask you a question about Star Trek. How did you get involved with the Star Trek universe? Have you met the cast? Have you met William Shatner? And what about Gene Roddenberry?
Well, yeah, I've the only cast member that I've actually met personally is George Takei, who plays, of course, Sulu in the original series and throughout some of the movies in the 1980s. And I had the good fortune of meeting him a number of years ago when he came out with his own biography, and he went on a book tour. And he came to Montreal, and I said, my goodness, I got to go out and see him. And I had the good fortune of talking with him a little bit. And it just really was very inspirational to having actually met somebody. I think I was really starstruck, if you can say that, having met him. And with this book project now, I'm still to meet. I mean, my dream is to meet the cast, and I will be going to Star Trek conventions in New York, the Mission New York, on September 3rd and 4th, where there's going to be many of the cast members there from all the different series, including William Shatner himself. And so I'm hoping that we'll be able to meet in person. My dream is really to make sure I have my book, my personal copy, signed by as many of the cast members as I can. But William Shatner, I included him in the foreword. When I finally found a home for the book with National Geographic, I told the folks there that I had to have Captain Kirk himself sort of set the scene for the book. I really wanted that. That was something extremely important for me. And because he's such a larger-than-life character, Captain Kirk, I mean, he's really a cosmic swashbuckler of sorts. And to me, he's kind of like an Errol Flynn type of character almost. And he really embodies the spirit of adventure. And so this is on the cosmic scale. And he personally is interested in science fiction and science as well. So we were very fortunate to get him. I said to his personal assistant I tell him that I'm from Montreal. I tell him I'm a fellow Montrealer, just like William Shatner is. I was born in Montreal, and we went to the same university, McGill University, and I guess that those appeals were successful because I landed him for the foreword.
Okay, now let's talk about the program itself. What was your favorite episode, an episode that sticks in your memory? What was one of the favorite episodes of Star Trek that you liked?
Wow, that's a big question of which ones are my favorite. But I think the City on the Edge of Forever really stands out, and I'm not the only one. I've talked to other fans too. It's from the original series, third season, and it's an episode that involves so many levels. It's just a beautifully done, beautifully written script.
It's a time travel episode, right?
I'm sorry?
It's a time travel episode, right?
That's right, exactly. It's a time travel episode, very well known because it has a guest starring...
Joan Collins, right?
That's right, Joan Collins, that's right, a famous actress, and she plays Edith Keeler, who's running this mission for folks, and in pre-World War II in the United States, and she falls in love with Captain Kirk, and it's a tragic romance because she does get killed, and of course Captain Kirk has to wrestle with this idea of can he save her, or should he save her, or just let her die? And of course logic prevails, and he has to let her die because if he does save her, then that will change the course of history. And so within that episode as well, there's this nice scene where they're out on a date and walking on the street, and Captain Kirk looks to the heavens and points out to Edith Keeler a star in the sky. And that star is actually one of the stars in the belt of the constellation Orion. It's a real star. And I have this memory of that as a childhood memory of watching that, and my father actually taking me outside and showing me that very same star in the belt of Orion. So there's this really deep connection that I have with that particular episode.
Well, you know, some science buff asked the question, what lies on the other side of a wormhole? Well, we know the answer. It's Joan Collins. Yes, she's on the other side of the wormhole, and that's how they go back into the past. Now let's talk about some of the science or lack of science in Star Trek. Whenever the Enterprise goes near a planet, the first thing Spock asks is it a Class M planet? That is it an Earth-like planet? Well, let's be real. Is there such a thing as a Class M planet, or is that just a fiction devised by Gene Roddenberry?
Yeah, I mean, that they had to come up with a hodgepodge mix of different kind of aspects of what a planet is to create what is an M-class planet. There is
Andrew, we have to take a short commercial break, but after the break we're going to continue a discussion of Star Trek, the official guide to the universe, because it is the 50th anniversary this September. Amazing. Our special guest today is Andrew Fazekas.
You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's the 50th anniversary of the Star Trek series. And to commemorate that, there is a new book, Star Trek, the official guide to the universe, which mixes science and science fiction. With us here today to talk about the book is Andrew Fazekas. He is commonly known as the Night Sky Guy, a science writer with National Geographic News. He's also with Canada's Weather Network and also a consultant for the Canadian Space Agency. Where we last left off, we were talking now about the science behind Star Trek. In Star Trek, they talk about Class M planets, which I imagine means Earth-like planets, but actually there's no such thing as Class M planets. However, the Kepler satellite orbiting in outer space has confirmed the existence of over 1,000. So, Andrew, the question is, did Star Trek get it right in describing some of these planets, given the fact that we now have an encyclopedia of over 1,000 planets orbiting other stars in the night sky?
They've gone into their own type of fictional planetary classification, that's for sure. And M-class, their M-class of planets is probably the most similar to what we're looking for, this Earth 2.0. Planets that have Earth-like qualities, specifically, in the habitable zone around the star where water can exist in liquid form. This is something, if you look at the fictional classification that they have, they were looking for planets. M-class planets would be ones that have an atmosphere that contains large percentages of nitrogen and oxygen. The surface would be abundant with water. Their cores would be made with things like nickel and iron, things that are pretty much analogous to what we're looking at in Earth terms. And Gene Roddenberry and his science consultants, which, by the way, were always used throughout all the different series, television series and movies, they came up with this fictional canon. But you have to remember, back 50 years ago, looking for detecting planets was out of the realm of possibility at the time. The scientists 50 years ago believed that planets would not be able to be detected because the light, the reflected light, would be way too feeble compared to their host stars. So we've gone really light years ahead in many respects of now having this Encyclopedia Galactica of all these planets that we're detecting through, of course, mostly indirect methods. And what's interesting is, I have to say, is that within the Star Trek universe, when they were trying to characterize M-class planets, many times the starship teams would have to send probes or teams down to the surface to really analyze it, to really determine exactly what class of planets. But their classification was very intricate, and our real-life classification planets are nowhere near there yet, because we just don't have enough information of being able to class them to, different. They had over almost a dozen different classifications in the fictional years, and we're nowhere near that with our knowledge yet. But that's yet.
Now, for fans of Star Wars fans knows that there is a planet with two suns, and many astronomers, I still remember, many astronomers at that time said, bah, humbug, a solar system with two stars and planets going around two stars would be inherently unstable, and therefore Star Wars got it wrong. Well, who actually got it right or wrong? Don't we actually have evidence now of planets in outer space going around a double star system? So the astronomers were wrong, right?
So, I mean, this is where it's interesting, where, you have this confluence of fiction and science coming together, right? So, but the two have always been intertwined. When we're talking about good science fiction, it always involves elements of true science. So in Star Trek, when you're looking at both Star Wars and Star Trek, I'm always being asked this, who did get it right? And Star Trek tends to appeal to the inner geek, I think, in most people.
Okay. Andrew, we have to take yet another short commercial break. But after the break, we're going to continue, and we'll have a discussion. Which would you prefer, Star Wars or Star Trek, in terms of who got it right? And
If you ask, you're listening to Science Fantastic with Professor Michio Kaku. Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, we have on the line with us Andrew Fazekas, author of the book Star Trek, The Official Guide to the Universe. And also, let me point out once again that I'm also on national tour. You can go to my website, mkaku.org, mkaku.org. Maybe I'll be signing your copy of my latest bestseller, The Future of the Mind. 2 years ago, it hit number 1 on the New York Times bestseller list. It's now in paperback form, The Future of the Mind. So find out about my tour schedule by going to mkaku.org or my Facebook site. We have almost 3 million people now on my Facebook site. Or on my Twitter account, we have about 300,000 people picking up my Twitter feeds. But today, let's talk about the 50th anniversary of Star Trek. Star Trek, The Official Guide to the Universe, is the book we're talking about today. The author is Andrew Fazekas. It has a foreword by William Shatner himself. It has over 400 full-color images, the science and science fiction. Well, that you began to answer before the break, and that is between the Star Trek fans and the Star Wars fans. Well, who gets it more correctly in terms of the science?
I love both of them. Star Wars, to me, though, is more of science fantasy than fiction. So for me, and it speaks to my inner geek, Star Trek is more something where I can see the future in terms of our humanity and technology and the science of playing out. Now, there are some things there that, maybe not even in our future, like, for instance, the transporter system or the warp drive, things like that. However, there are so many other sciences like the astronomy, the cosmic canvas that's in the background. Star Trek tends to get it right, but if I'm not saying Star Wars doesn't have it beyond the space opera that it is. You look at some of the worlds, some of those planets that are there as well. As we had mentioned, Tatooine being the prime example, there are things that now science is bearing out that can exist, and the producers, the makers of these films, are now trying to incorporate real science discoveries to flesh out this canvas, this astronomical canvas that the space opera plays out on.
Okay, so let me ask you a question. Oh, we have to take a short commercial break, but after the break I'll ask you a question. What was right and what was wrong in terms of Star Trek? Where did Gene Roddenberry get it right and where did he get it wrong?
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about the 50th anniversary of the Star Trek series. And so before the break, we had a question. What did Gene Roddenberry get it right? Where did he get it right in the series Star Trek? And where did he get it wrong?
There's so many different things, right or wrong. Astronomically, if, maybe perhaps what they might have missed. I think one of the glaring ones was quasars. Quasar, stellar, these magnificent stellar objects that are basically these very strong active cores of galaxies that are literally hundreds of millions, if not billions of light years away. They were portrayed in the Star Trek universe, particularly in the original series back in the 60s, as objects within our own Milky Way galaxy, a sort of a stellar type of object, a star-like object. One particular episode is the Galileo 7 back in 1967, and you get to see what the object looks like, and it's nothing like what a quasar is, which is a much larger galaxy. It's an actual galaxy itself that's billions of light years away.
Yeah, but I remember back in the 60s, there was a legitimate debate among astronomers. There was a faction of astronomers who did think that quasars were very nearby, and that would explain their redshift, rather than being very, very far away. So, there was a debate back then.
There was a debate, exactly. There was a debate on what, and I think, Roddenberry and his team of writers had to make a decision of which way they were going to go. Now, of course, as time, it's kind of unfair because now with time, right, it's borne out that they are, extragalactic objects. But that was something that is interesting because if you look at the episodes today, they've been remastered. And the visual aspects of what the quasar looks like, they've changed it over time, which is really interesting in the remastered version. It's worth looking at in the Galileo 7 episode. And then one of the ones that I really enjoy looking at is, again, in the original series, and it's been remastered to look absolutely amazing, but they got it right the first time, is All Our Yesterdays. And All Our Yesterdays in 1969 was really about this impending supernova explosion, this giant star that explodes. And they had to save people on this planet that's orbiting this impending supernova explosion. And it's just wonderfully, it depicts how the explosion occurs on screen. So that's one of the places that I think, astronomically speaking, they got it really right.
Well, one of my favorite episodes is in the Next Generation, where they pick up a time capsule from the past containing dead people from the 20th century who were frozen, hoping to be thawed out in the 23rd century or so when there's a cure for cancer. So they thaw out a banker. And he realizes, oh, my God, it's the 23rd century. I'm rich. My investments are worth a fortune. I'm rich. And then he talks to the crew of the Enterprise to track his investments. He must be a billionaire now. And they look at him and they say, what? What is money? You want something? You simply ask for it with the replicator. which I thought was very seditious, right? In the future, if you want something, you simply ask for it.
Yeah, and you know what? That you mentioned that episode. It reminds me, of course, of the Wrath of Khan, right? Because if you think about the original, where they brought that character in the original series, there again, that was a group of humans that were in suspended animation from going back into 1990s in that script, and they had reanimated them. Of course, they were in a different time period completely, and that went on to be the showcase in Wrath of Khan in 1982 in the movie.
Now, what do you think was perhaps the most egregiously wrong thing on Star Trek? You mentioned that they got supernovae, they got some of the planets, they talked about the universe and its glory. Was there anything that really made you cringe?
Well, you know what? The concept of warp drive is something that I wish we would have, but we don't. And the transporter system of breaking ourselves down to molecules and then rebuilding it on the other side. It's obviously these are plot devices that make the story move ahead. And I can look at it on the side, but the inner science geek in me kind of cringes going, I wish that we could have it. And then I know we're getting there in certain rudimentary ways with photons of light and, applications for quantum computing and stuff, but actually being able to transport ourselves like that, and then, of course, the warp drive of going at those tremendous speeds, that, I think, is something that, it'd be interesting to see where we go in the future with those technologies.
Well, Star Trek takes place in the 23rd century, and before we have warp drives, we may be perhaps 1,000 years off. But it is conceivable that within 1,000 years, we may have enough energy to play with black holes and to warp space-time to the point where we have warp drive. But it's not for us. We're maybe 1,000 years behind the energy technology necessary to manipulate a warp engine. And teleportation, as you said, we can only teleport photons and atoms of cesium, rubidium, but not much more than that. So I think we're still a long ways from that.
And would you want to be teleported? That's the big question. If you had is that something that sounds like it would be a good idea?
Oh, like in what sense? I mean, who wouldn't mind being able to, teleport across long distances in an instant? But what are the drawbacks?
Well, I don't know. I mean, to me, it also speaks to the idea of if you have a soul, for instance, if you're being dematerialized like that, broken down into little bits of atoms and being rebuilt, I don't know. That sounds. I'm like Leonard McCoy, Bones. It kind of irks me. I don't know.
Okay. Well, unfortunately, that's it for Science Fantastic. Once again, you've been listening to Andrew Fazekas. The book is called Star Trek: The Official Guide to the Universe. So, Andrew, thank you so much for being on Science Fantastic.
My pleasure, and live long and prosper.
This is Science Fantastic.